In the last class, you have seen that we are talking about the non-smooth or border collision bifurcations, and you have seen that these happen when the slope or the Jacobian matrix slope in case of a one dimensional system or the Jacobian in case of higher dimensional system that changes abruptly. For example, if there is a map whose graph would be of this form x n versus x n plus 1, something like this. So, here the slope changes abruptly. So, in case the situation is that this is the fixed point, as you change the graph of the map with change of some parameter, if it so happens that the fixed point is now here, the point of intersection with the 45-degree line is now here, and suppose with the change of the parameter it moves like this and at some point it goes like this, then obviously at this point the slope abruptly changes, therefore, the stability status will also change abruptly, and the resulting bifurcations were called the border collision bifurcations. And then we said that in order to probe the quality of these bifurcations, we will need to look at, there is no need to look at all these areas of the map, rather it suffices to look at only the local linear neighborhood. And then we said that let the map be then given by x n plus 1 is equal to a x n plus mu for x n less than 0, is it visible? Yes, and b x n plus mu for x n greater than 0. So, this was the map that we had considered. As a result, the A side is the slope, these are piecewise linear map. So, A side represents the negative side, sorry I will have to put it differently, the 45-degree line, A for x n less than 0. So, represents this kind of a slope and B represents this kind of a slope. So, it is a piecewise linear map. Probably you are now able to see the link between this map and the map that we had considered while talking about the Frobenius-Perron operator, that was a piecewise linear map. So, that occurs in many physical systems. So, we are out to understand what happens for different values of A and B. And then we said that we can draw a picture of the parameter space A versus B parameter space, and for A less than 1 over this range it will be one type of behavior in the left hand side, and for B less than 1 and greater than minus 1 there will be another type of behavior. So, in this box where this is minus 1, this is plus 1 and this is plus 1 and this is minus 1. In this box, which means A ranges between minus 1 to plus 1 and B ranges between minus 1 to plus 1, you expected a stable behavior as the fixed point moves across the border. Okay. So, this point would be called the border, because that represents the borderline between two different types of behavior. So, that is where we were. We had explored this part. Just to recall what happens in this part, it was, if you draw the bifurcation diagram, it would be something like this. So, I am now drawing the bifurcation diagram. It would be a stable fixed point approaching and then at this point hitting the border and then again going off as a stable fixed point. Okay. Because in both sides, in the left hand side as well as in the right hand side, the slope is less than 1 and therefore, the fixed point will be stable. Okay. So, these are reasonably easy situations to handle. So, this is your mu and this is your x. So, this would be the behavior in this part. What will be the behavior in this part? As we had concluded, the graph of the map would look something like this. For example, if you have somewhere here, the graph of the map would look like, how would it look? A value greater than plus 1. So, it will be something like this, and B value like this, negative, B value negative, but greater than minus 1. So, as you can see, as this graph of the map, so this is x n versus x n plus 1, it goes up as you change the parameter mu, it goes up. So, at a specific parameter value, it would go into a situation like this. Before that, there would be no fixed point, and at this point 2 fixed points will be born, this one unstable and this one stable, right. So, in the bifurcation diagram, if you draw the bifurcation diagram, you would expect there to be no fixed point before the border collision occurs, but at this point a pair of fixed points will be born like this. So, this is similar to the saddle node bifurcation that you have already come across in all senses, except for that earlier we have seen that this would be a smooth curve, now this is a kink, that is all, not a big deal though. We have also seen that in this part both the fixed points are unstable. Even if both the fixed points are unstable, there can be stable orbits, not a periodic orbit, but a chaotic orbit is possible, because there would be a trapping zone in the graph of the map, so that any point inside the trapping zone maps inside the trapping zone, so that any initial condition cannot escape. So, okay, we had come up to this stage. So, we decided that a situation like this both the sides will have slope greater than unity. This will become stable so long as this point maps like this and it maps to a point that is inside, but it will become unstable where this point maps to a point that is outside. That is what we have decided. And from this condition, it is very simple to obtain the condition for which the chaotic orbit will remain stable. Have you obtained that? Have you obtained that? The position of this point is what? Notice that this is the value of x n plus 1 for x n equal to 0. So, if you put x n equal to 0, both give mu, right. So, this point, this height is mu. The next, what are you asking? Where does mu map? So, if in some iterate x n equal to mu, where does it map? So, just put it here, it will map to this side. So, put it here, b mu plus mu, so you put it here and you find out where it maps. If you do that, you will find that this will have a curve like this, where this curve is given by minus a by a minus 1. Minus a by a minus 1. I am leaving this proof to you, just I am writing the value. So, we have come up to this stage. What happens for this part? Now, let us take up this part. What does this represent? A value between minus 1 and plus 1 and B value less than minus 1. So, what will the graph look like? The graph will look like A value between minus 1 and plus 1. So, let us say like this, and B value greater than or less than minus 1. So, something like this. Now, here you notice that before or for mu less than 0, the graph would be something like this. At this point, it will hit and then it will go off. When it is less than 0, that means when mu is less than 0, mu less than 0 and mu greater than 0, then this is the fixed point and the slope is less than unity. Therefore, this fixed point is stable. you might notice that if you take this as a pair of sticks and if you raise it, this point will move progressively to the origin. So, in the bifurcation diagram you would expect that the fixed point will move in position, and at that point the border collision takes place. What will be the result after that? You would notice that after that the fixed point becomes this one, and at this one the slope is less than -1. So, it will be unstable. Good. If it is unstable, what will be the behavior like? What will be the behavior like? Now, if the fixed point is unstable, from our idea about the smooth systems, that means where the behavior was something like this, we have studied that like a logistic map, and when this slope becomes less than -1, what did we expect? A period doubling. So, here also it is natural, intuitive to expect that, but we will need to check whether it really happens or not. How do we check? How do we check? The first question is, does the period 2 orbit occur at all? That means, does it exist? In order to check that, we will need to do this, that we will say if there is a period 2 orbit, how will it look? It will have one point here and then it will go like this, right. So, one point in the left side, another point in the right side. Suppose you start from here, that means x n plus 1 is equal to a x n plus mu, that has brought me to the right hand side. Then we say x n plus 2 is equal to b x a x n plus mu, I am substituting x n plus 1 plus mu. Okay. Now, in order for the fixed point to exist, this must be equal to, that is the condition for the fixed point. I started from x n, went to x n plus 1, went to x n plus 2, and then said if this is equal to x n, then the period 2 orbit, that is the condition for the period 2 orbit. So, we have got a expression that we can solve, right. So, what do you get? A b x n plus b mu plus mu is equal to x n, right. Bring it to this side. Is it right? A b minus 1 x n is equal to minus mu b plus 1, right. So, we have the position x n given, and let us see what is the condition we are getting. Okay, this is the condition under which it will occur. You might simplify it later, but I am just showing you the way to obtain the condition for the occurrence of this fellow. Good.
If A is between 0 and minus 1.
What?
So, in this same case,
Huh?
if A is between 0 and minus 1.
A is between 0 and minus 1, then the graph will look like this, right. That means, in this case it is like this, in this case it will be like this. No important change will really occur, because here also this will be the fixed point and its slope will be stable. So, there will be no important difference though, that is why I am not going into that. But now notice that we had started from a point in the left hand side, went to the right hand side and came back to the left hand side, therefore, x n must be negative. So, this fixed point will exist if the x n value obtained from here is negative. Similarly, you can start from a point in the right, go to the left and come back to the right, obtain a similar condition, that will be positive. So, that will be the condition of existence. If you do that, you will find that over the whole range, the period 2 orbit really exists. Over this whole range, the period 2 orbit exists. but then will it be stable? What will be the condition for stability of the period 2 orbit? There is one iterate to the left side, another iterate to the right hand side. Here the slope is A, here the slope is B. Therefore, the slope of the period 2 orbit will be AB. So, in order for that to be stable, the AB magnitude has to be less than 1. So, AB magnitude has to be less than 1. So, condition for stability is AB less than 1. AB less than 1 actually gives two conditions, AB equal to plus 1, AB equal to minus 1. So, naturally we can expect if I draw this part here afresh. So, we are now drawing only this part. So, that here this point is A and this point, this side is B, and here it is minus 1, here it is 0, plus 1, minus 1. So, this is a box that we are really drawing. AB less than minus 1, we will have two curves therefore. One will be like this, another will be like that. Okay. This will be the curve for AB equal to minus 1, and this will be the curve for AB equal to plus 1. Right. In order for AB to be plus 1, both A and B have to be negative. This is the side where A is negative, and therefore, this is the side where B is negative, both are negative. So, this is the curve for plus 1. What happens here in this part? In this part, we understand that the period 2 orbit will occur. If we now draw the bifurcation diagram, how will it look? X here, sorry, mu here, X here. It will be stable so long as the point is moving towards this point, and then at this point it becomes unstable, and the period 2 orbit then becomes stable, but its behavior will be a bit different. It will be like this. It will not be the typical this shape that you have seen. So, that is again it is a period doubling, but caused by a border collision. Well, now so this part we understand what will happen for these values of A and B. In this part what will happen? The period 2 orbit will exist, but has become unstable. Now, if period 2 orbit becomes unstable, what is the next intuitive reasoning? Well, period 4, wait. But in that case, we need to justify why period 3 orbit will not be possible. Now, in case there is a fundamental difference between the smooth map and non-smooth map, that in case of non-smooth map, that is also possible. We can easily check. What will you have to do in order to find out the region of existence of period 3 orbit? All we need to do is that there will be one point to the left, another point to the left, and this another point to the right. So, you will take this map, and you will come back here. You can easily find out the algebraic condition for which this will occur. Okay. And what will be the stability condition? A square B less than 1, because there are 2 points to the left and 1 point to the right. So, if these conditions are satisfied, this fellow will exist. One will be the stability condition, another fellow will be the existence condition. So, you will get again a range for which this condition will occur. There will be another range for which the period 4 orbit will occur, another range for which the period 5 orbit will occur. As a result, you would notice, let me show you the actual pictures. Is it visible now? Yes. In the AB parameter space, in this part, all these different orbits will occur like this. The white regions are the regions of occurrence of different periodic orbits. Here it is period 2, here it is period 3, here it is period 4, here it is period 5, here it is period 6, and so on and so forth. But in between, no periodic orbit really can occur. So, what can occur in between? Chaotic orbit. As a result, here we see come across a typical situation that is often encountered in engineering systems, a period adding cascade. That means, as you increase the parameter this way, what do you observe? A period 2, then a thin range of chaos, period 3, again a thin range of chaos, again a period 4, again another range of chaos, period 5, again another range of chaos, and so on and so forth. Okay. That is a period adding cascade, not a period doubling cascade. This is one of the typical things that can happen in non-smooth systems. Let me illustrate this on the computer. Okay, so we have chosen C3, I will choose as minus. Okay. Now, here you notice the behavior, can you see? Here there is a period 2 orbit. No, here there is another, that means this is a period 3 orbit. There was a period 2 orbit. At the top there is a period 2 orbit, here there is a period 3 orbit, again it is a bit of chaos, period 4 orbit, again a bit of chaos, period 5 orbit, again a bit of chaos, period 6 orbit, so on and so forth. Okay. So, this is called the period adding cascade that can happen in this kind of systems. In fact, they have been observed in many electronic circuits where there is some kind of a switching phenomenon. Clear? So, we have more or less worked out the whole situation here. So, we understand. Again, let me recapitulate what happens here. Period 1 orbit remains stable. What happens here? Like a saddle node bifurcation, a period 1 orbit stable and another period 1 orbit unstable are born. What happens here? 2 orbits are born, both are unstable, but there can be chaotic orbit here. In this part, what can happen? 2 orbits are born, 2 periodic orbits are born, both unstable, but the resulting chaotic orbit is also unstable. So, this will happen here, and in this part there can be a transition from periodic orbit, period 1 orbit to period 2 orbit, or a period 3 orbit or period 4 orbit, all these are possible. Okay. That means, here you see I have moved it like this. I have let us come back, I have moved the parameter like this with mu held positive. So, that is why you are getting this diagram. Now, if say I choose the range here, for example, in the period 3 range, then what will be the bifurcation diagram like? It will be period 1 to period 3 as mu is varied. If I choose a parameter in the period 4 range, what will be the bifurcation diagram like? 1 to 1, 2, 3, 4. Okay. So, all these are then possible. So far you had the understanding that these are very, I mean, one would not expect, but in non-smooth systems these are also expected. Yes, period 2 can also happen.
So, sir, the same graph, I mean,
Huh?
in bifurcation, bifurcation, we take 1, then 2, then 4.
Yes.
So it is not, it won't be like 1, 2, and then 3.
No, no, no. Here we are talking about a single border collision event as mu is varied. Since both the sides are linear, then nothing can happen after this. For mu less than 0, there will be one type of behavior. For mu greater than 0, there will be another type of behavior. It cannot be anything that happens after this, because here we are not considering the nonlinearity in each side. But actually the system will be nonlinear in each side. So, there can be things happening in the other parts, but you cannot say that there will be a succession of these. But in realistic systems, see, here we are considering a system with this specific algebraic representation. Here we have modeled it in such a way that A, B are parameters and mu is such a thing that when it is varied, then you get a border collision. But in a real system, nothing is really modeled like this. It may so happen that you have a parameter, if you change that, only B changes, not mu. It is possible. And if that happens, for example, here in this diagram that I have just shown on the computer, I have changed B. As a result, you do see this cascade, period adding cascade, and that is exactly why the period adding cascades are reasonably commonplace in many physical systems and engineering systems. Okay, is that understood why period adding cascades occur? By the way, this is one of the mechanisms of period adding cascade. There are others, but I will not get into those complications. Okay, now so far we have been considering one dimensional systems. There is no reason to believe that every system is one dimensional. So, we also need to encounter the situation where there is a 2D system, and as you change a parameter, there is a border collision. How can that happen? It happens like this. Supposing this is the state space, and in the state space there is some kind of a border line like this, so that in this part there is one type of description, and in this part there is another type of description. So, if here is a fixed point, if you change the parameter, it moves and say hits the border, then at this point, if you obtain the Jacobian here and the Jacobian here, you will find that the Jacobian has abruptly changed as it hit the border. So, that is the position of the border collision. And here also, in order to understand it, we will need to do a local linearization here and a local linearization there. It has been shown that this local linearization, I mean, it will be very convenient to do some coordinate transformation, so that this border line becomes orthogonal. So, that let us look at only this kind of a reoriented state space that only comes from a bit of coordinate transformation. So, no big deal. As a result, the map itself can be expressed in the very convenient form, where x n plus 1, y n plus 1, this will be expressed as here there will be matrix x n, y n, and there will be a parameter like this for x n less than 0, and there will be another matrix x n, y n plus mu 1 0 for x n greater than 0. What are these matrices? Now, these matrices in the very convenient normal form are expressed only in terms of the trace and the determinant of this Jacobian matrix. So, normally what you do? You calculate the Jacobian matrix here, and from the Jacobian matrix you can extract the eigenvalues. The addition of the two eigenvalues is the trace, the product of the two eigenvalues is the determinant, and the matrix can be suitably modified only in terms of these two things. So, this is the left hand side, we will say tau L, L for the left hand side 1. Notice that in this form, what is the trace? tau L. What is the determinant? Delta. Okay. So, it is very conveniently expressed in terms of just two numbers. And here also it will be the right hand side. So, even though the representation in 2D looks, I mean when you just look at the picture and try to figure out how will it look, it may look a bit complicated, but actually it is not all that complicated. We can express in this very convenient form. So, here there are a few terms, parameters. In case of 1D there were A, B and mu, 3 parameters, but here you have 2 parameters on the left hand side, 2 parameters on the right hand side and a mu parameter which when varied it goes across the borderline. But now the state space for this is very conveniently expressed as this. The borderline is just vertical along the y axis. So, this is the left hand side and this is the right hand side. And you would notice that as you change the mu, vary the mu from a negative value to a positive value, a fixed point crosses the border like this. You can calculate the fixed point and you can easily do this. For example, how will you calculate the fixed point? Simple. If you have the fixed point in the left hand side, then you would have to calculate from this equation x n plus 1 y n plus 1 is equal to this. How will you calculate? Simply by making x n here and y n here, you can solve it and you can obtain it. That way if you do, you will see that I'll represent it with star, because the representation of fixed point is generally with a star. For the left hand side it will be, so this fixed point is given by mu 1 minus and this is really trivial. I am just saving time by not asking you to obtain it, because we have only a very little time left for this semester. That is why I am sort of saving the bother of calculating. So, this is the fixed point, right? When will it occur? See, this has been calculated using the expression on the left hand side. Therefore, if the x coordinate is negative, then only it will occur. Okay. Similarly, the one that is calculated from the right hand side equation is like this. Because of symmetry, I can blindly write it as fine, and this value will occur if the x component is positive. Fine. Seen from this angle, so in the left hand side there is a fixed point, say there is a fixed point. What is the character of this fixed point? We have learnt that the character of the fixed point is given by the eigenvalues. Okay. Character of the fixed point is given by the eigenvalues, and in this case the eigenvalues are can it be seen? Yes. So, if you calculate the from this equation, from this the eigenvalues, they are obtained simply like this. So, if these are real and between -1 and +1, you know that it is a stable thing. if these are real and less than -1, one of them is less than -1, you know it is a flip saddle. If it is greater than +1, you know it is a regular saddle, and so on and so forth. So, this fixed point, you can identify the character of the fixed point depending on the relative positions of the trace and the determinant. Is that clear? Now, this fellow, as you change the parameter, moves and becomes another fixed point here. When it becomes another fixed point here, that means the character must have changed because it has gone from one side to the other. Again you can calculate the character of this fixed point. So, it is again categorized as either at the regular attractor or a flip attractor or a regular saddle or a fixed saddle or a spiraling orbit, whatever it is, but it has a specific character. So, suppose we want to find out which type of fixed point goes and changes into which type of fixed point. We need to categorize this, and since the eigenvalues are given by this, a little bit of manipulation will tell you that we need to find out under what condition will it be stable, under what condition will it be real. Can you see under what condition will it be real? This term should be positive. In other words, the trace should be between -2 root delta to +2 root delta. Look at this. So, in this range it will be complex, outside this range it will be real. So, we can say suppose this is the trace and I am, this is the 0 and I am sort of comparing with the determinant, then we can say that there are two ranges -2 root delta and here the +2 root delta. In between this range it is complex. Fine. When is it stable? Stable means its value has to be between -1 and +1. All you need to do is to equate this to -1 and obtain this. Again you have to equate this to +1 again and obtain this condition. If you do that, you would notice that there are two conditions. This is -1 plus delta and here is 1 plus delta. So, from here we can get a picture representation. If I place my point here, what is the character? Stable and spiraling is inwards. If I place my point here, is it stable, but it is between 2 root delta and 1 plus delta. That means it is no longer spiral, but so long as it is below 1 plus delta, it is stable. So, what is the character in this range? What are the eigenvalues? The eigenvalues would be in this case real, but less than unity. Real and less than unity means regular attractor. So, in this part I will say regular attractor. In this part I would say spiral attractor. In this part I would say, what is it? Negative, eigenvalue would be negative, which means it will be a flip attractor. In this part it is positive, but the value will be greater than 1. So, it is regular saddle. Is it visible? I will have to write larger, and in this part it is flip saddle. So, when you write down the equations like this, then in each side the character of the fixed point will be determined by the magnitude of the trace as compared with the magnitude of the determinant on this line. But we are considering a specific type of fixed point turning into another specific type. So, this thing has to be done in two directions. So, we can now shape it like this. So, this is the trace in the left hand side and suppose this is the trace in the right hand side. So, the trace in the left hand side will be compared with these lines. So, this is minus 2 1 plus delta 2 root delta plus 2 root delta 1 plus delta and so on and so forth. Similarly, the trace in the right hand side will be again compared with similar things. This is 1 plus delta r, this is 2 root delta r, this is minus 2 root r minus 1 plus delta r. Good. Which means now, if I place the pen anywhere, say here, it will mean a specific relationship between the trace and the determinant in the left hand side as here, a specific relationship between the trace and the determinant in the right hand side like here, which means a specific type of fixed point turning into another specific type. If I place my fixed point my pen here, what does it mean? The trace in the left hand side tau L is between minus 2 root delta to plus 2 root delta. That means, while in the left hand side what was its character? A spiral attractor. Okay. While it has gone to the right hand side, what is its character? It is here as compared to this. It is again minus 2 root delta to plus 2 root delta. That means, a spiral attractor remaining a spiral attractor. Similarly, if I say put my pen here, what would it mean? As far as the trace in the left hand side is concerned, it is between minus 2 root delta to plus 2 root delta, means it is a spiral attractor. Here it is less than minus 2 root delta, between minus 2 root delta and minus 1 plus delta, which means a flip attractor. Which means, if the parameter is placed here, a spiral attractor hits the border and turns into a flip attractor. Now, this picture sort of more or less resembles the picture that we have drawn earlier. Only in this case, these were simple plus 1, minus 1, A, B. Here you have a little bit of complication, but it is not difficult to see that as delta becomes 0, this becomes plus 1, this becomes minus 1, this becomes 0. So, as you change the delta to 0, these ranges shrink to 0. That means, the range for which spiral attractors occur shrink to 0, and you get the exactly same picture. That is why, while comparing these two, you should remember that a one dimensional system can be represented in 2D with determinant equal to 0. Same thing really. Trace is similar to the slope. A and B in this case are same as the trace. So, often by looking at the matrix, we cannot figure out what would it be if it is really representing a 1D system. Yes, you can do that. In that case, the determinant would be 0 and the trace would be similar, equivalent to the slope. Now, I will not get into the details of all that happens in these parts, because there is no need to. We have more or less understood that there can be 3 distinct different types of behavior as seen as understood from the one dimensional case, which is simple. Here also the same basic types occur. Basic type means 1, fixed point remains stable. 2, and 3, These are the three possibilities that can happen. Now, in comparison or in contrast to what we have learned in 1D systems, all these have further sub cases which I will not go into, but just let me give you a glimpse of what can happen. For example, when a fixed point hits the border and becomes unstable, something else becomes stable. Now, what can become stable? We have learned that a period 2 orbit can become stable, a period 3 orbit can become stable, or period 6 orbit can become stable, or a chaotic orbit can become stable, so that you can have the transition from a period 1 orbit to maybe a chaotic orbit like this. This we have seen, right? That means it could be a period 1 to period 2, it could be a period 1 to period 5, it could be period 1 to chaos. A direct transition from period 1 to chaos is then possible. We have seen that when a pair of fixed points are bound, one can be unstable, another can be stable, a case which is reasonably well understood. Both could be unstable. If both are unstable, there is a possibility of having a chaotic orbit. Here also that happens. The only thing is that normally you have seen when we were talking about the smooth systems, for example, the logistic map, you have seen that the periodic orbit becomes period 2, becomes period 4, becomes period 8. This is the standard picture for the logistic map, and then there is a chaotic orbit. But then the chaotic orbit is punctuated by a period 3 window, which again goes to like this, and again a chaotic orbit, and so on and so forth. And in these chaotic orbits, you have seen that there are tiny periodic windows, right? We have seen that. And if you choose any parameter here, there is a theorem that says that in arbitrarily closed neighborhood there could be a periodic orbit. But here in such systems, no. In such systems there would be a large range of parameters over which the chaotic orbit will be stable. That means there is no periodic orbit around. Such orbits are called robust chaotic orbits. In fact, wherever we consider practical application of chaos, for example, nowadays there are various practical applications of chaos that are coming up, including areas in which we look at spreading the spectrum. Spreading the spectrum is useful in electronic circuits, power electronic circuits, cell phones, CDMA kind of transmission. There also the same things are useful, but remember, if you are aiming at an engineering application of chaos, it has to be robust. I mean, you cannot really have a situation where tiny undesired perturbation in the parameter will get it out of chaos. No, you cannot have that. So, it is necessary to have robustness in the chaotic behavior, and that is possible in this kind of non-smooth systems. So, this is something we have understood, this is something we have understood in sort of very sketchily nevertheless, but nevertheless we try to understand what is the essential issues. Here a fixed point remains stable. That means, if you draw the bifurcation diagram, you would expect something like this to happen. A fixed point was there, hit the border, and it remains stable. Initially, when the theory developed, people thought that this is the desirable situation in any given engineering system. That means, if you are in an engineering system, you expect a border collision to happen, this is the kind of situation you should aim at, so that the system does not get destabilized. Okay. But we have found then that there are situations where other periodic orbits are born at the same time. That means, while this fellow was stable, another periodic orbit was born at this parameter value. You might ask, so what? Just imagine a practical situation which is undergoing this kind of a transition. You are approaching this critical parameter value. Suppose you are changing the parameter. Just following this critical parameter value, the bifurcation point, what will happen? There will be two attractors existing. and they are arbitrarily close to each other. Can you see that? Now, in any real system there is some kind of a noise, so that due to the noise there will be some oscillation, and there are two orbits that are arbitrarily close to each other. What does it mean? It will keep on jumping between the two orbits, and as you change the parameter their distance increases, and finally the fellow gets locked to one of them. Which one? There is no guarantee. There is no guarantee, and it is not difficult to see that there is a fundamental source of uncertainty as to which one it will lock to. So, this is a typical situation that can happen in non-smooth system that people have come across. There is another situation where there is the fixed point goes and it remains stable, but what is born along with it is not another periodic orbit, but an unstable periodic orbit. That means, if you have an unstable periodic orbit, then you know that its stable manifold causes a basin boundary. So, what will happen is that this orbit will have a basin of attraction. Here also this orbit will have a basin of attraction. Now, what happens is that this orbit had a basin of attraction, this orbit had a basin of attraction, fine. Everybody would think that, so what? What happens is that basin of attraction shrinks to 0 at this point. That means, the region of the state space from which points are attracted to this attractor shrinks to 0 at the point of bifurcation. As a result, even though the fixed point remains stable, if you calculate the eigenvalues it is stable, yet any initial condition will go to 0, go to infinity at this bifurcation point. This situation has been called the situation of dangerous bifurcation, because the dangerous bifurcation because there is no signal. You keep on monitoring the eigenvalues of the system, it is stable. Always you will get a signal that it is stable, the system is going to remain stable, yet the system collapses. Okay. So, all these possibilities are there in non-smooth systems, and as I told you, non-smooth systems are very common in physical world and as well as in engineering. For example, power electronic circuits are non-smooth systems where there is switching. Any switching circuit for that matter is a non-smooth system. Human heart is a non-smooth system because of the opening and closing of the valves. There is also a switch in hydraulic domain. Walking robots, these are also non-smooth systems. Why? Because the one foot down, another foot up, another foot down, another foot up. These will have to be represented in terms of some kind of set of differential equations, and it is not difficult to see that this set when this foot is down, another foot is up, is different from the situation when both the feet are down, and the critical parameter value is where it is just making contact. So, all these possibilities are there. So, in order to understand the behavior of such systems, we need to understand the theory that we just talked about. Okay. That is all for today. We will try to finish whatever remains in the next class.